I am Aditya Agarwal, and today I'll be presenting our work titled Towards Automating Retinoscopy for Refractive Error Diagnosis. This is a joint work in collaboration with the Shankara Eye Hospital. Refractive error is the most common eye disorder. It happens when the optical system of eye is unable to focus light on the retina. For example, as shown in the figure, in normal vision, the eye focuses objects perfectly on the retina, while in case of myopia, the focus point is in front of the retina, and in hyperopia, it is behind the retina. Although refractive error is very common and may seem like a solved problem, it turns out that this condition goes undiagnosed for many people worldwide. According to a 2015 study, undiagnosed refractive error was responsible for vision impairment in approximately 128 million people worldwide. And out of the 36 million blind population, 20.6% were blind simply because of undiagnosed refractive error. There exist multiple methods to diagnose refractive error. First is the gold standard and most accurate method using the vision or logMAR chart. This is a subjective method where the patient has to subjectively assess their vision. Although accurate, the main drawback of the method is that it requires a lot of patient cooperation, which makes it challenging for young children. The second method is an autorefractor. This is an objective method which does not require subjective assessment by the patient. The biggest advantage of this is that it is automatic and requires less patient cooperation. However, these devices are expensive and prior studies show that they exhibit higher errors. The next method is retinoscopy. This is also an objective method like autorefractor. The biggest plus is that it requires minimal patient cooperation and can be used even for infants. It is much more accurate than autorefractors and can also be used to screen other eye disorders. However, it is a time-consuming process and requires a lot of expertise to perform retinoscopy. Our proposed solution to democratize refractive error diagnosis is a smartphone-based system for automating retinoscopy. Such a solution alleviates the need of high skill requirement and increases the portability of manual retinoscopy by getting rid of the lens kit. During retinoscopy, the optometrist shines a beam of light from the retinoscope on the patient's eye and observes the speed and direction of retinal reflex formed in the eye. When the patient has a gross positive power, the reflex moves in the same direction as beam and is called with motion. If the patient has a gross negative power, the reflex moves in the opposite direction and is called against motion. If the patient has a zero gross power, the reflex completely fills the pupil, and this is called neutralization. This is the end stage of retinoscopy. The retinoscope itself is a reasonably simple optical instrument. There is a light source at the bottom. The light from the bulb passes through a converging lens to a beam splitter. The beam splitter reflects half the light towards the patient. The patient then gets a perception that the light is coming from behind the retinoscope. In the forward pass, the beam from the retinoscope passes through different optical components of the eye and gets focused on or near the retina, thus illuminating a small portion on it. In the backward pass, this illuminated portion acts as a light source. The light again passes through eye's optical system in reverse order and through the retinoscope's beam splitter into the examiner's eye, or in our case, into the smartphone camera. The image of this portion of retina is referred to as the retinal reflex. After solving for the optics of forward pass, backward pass and the image space, we reach a simple formula for refractive error as shown here. The three variables U, D and R in the equation are as follows. U corresponds to the effective light source distance. It is a property of retinoscope and can be computed from retinoscope specifications. D is the working distance, that is, the distance between retinoscope and the eye lens plane. R is the main variable from the retinoscope functioning. It is the ratio of reflex velocity to beam velocity. Now, there are three variables which needs to be computed from a retinoscopy video: the working distance, beam velocity and reflex velocity. However, there are multiple problems in this. The beam moves on an uneven surface, the eyebrows, eye socket area, etc. So it is very hard to localize the beam. The other problem is that since the camera itself is moving, it is very hard to compute the velocity of beam and reflex with respect to a fixed reference frame. Third, the working distance is also not apparent from the video either. To solve these problems, we use a very simple and frugal solution. We ask the patient to wear a paper frame while recording retinoscopy videos. The paper frame has squares placed at fixed places called as fiducial markers. Actual size of fiducial markers along with the known camera parameters are used to estimate working distance in the video. Paper frame is also fixed with respect to patient and hence is used to localize a world coordinate frame. Here is an overview of the video analysis pipeline. We first extract the region of interest, then we detect the fiducials via edge detection. After detecting position of fiducials on the paper frame, we compute homography to do perspective correction. Now since we have a known virtual coordinate system, we localize the region between top two fiducials to identify the beam edges. Similarly, we focus in the blue box to detect pupil and the reflex edges. Please refer to the paper for a more detailed explanation on the pipeline. Here is an example of a processed output. As you can see, the fiducial detection, beam detection, pupil detection and reflex detection is quite robust. We evaluated our system on 185 distinct eyes obtained from 128 patients with a mean age of 30. Here is a correlation plot of the predicted refractive power from our system versus the ground truth obtained from subjective refraction. The mean absolute error of the prediction was 0.75 diopters. Note that 43.2% of our predictions were within 0.5 diopters, while 74% were within 1 diopters. We also evaluated the use of our system as a screening classifier, where we categorize predicted powers in the range of -1 diopters to 1 diopters as normal and flagged the other cases. We obtained a sensitivity of 91% and specificity of 74%. We also present a finer grained evaluation in different refraction error ranges as shown here. Going forward, we want to make multiple improvements in the system. Right now, we collected data with a head chain rest and tripod arrangement. In future, we want to work with a freeform setting with just a handheld retinoscope. Currently, our system predicts net refractive error along the scope meridian. However, we are working on a formulation and video analysis pipeline to handle cylindrical errors as well. Lastly, retinoscope can also be used to detect keratoconus. In keratoconus, the cornea is distorted from a normal shape to a conical shape, resulting in eye not focusing on single point. As a result, during retinoscopy, multiple reflexes are formed, which is referred as scissors reflex. We plan to modify existing video analysis pipeline to detect scissors reflex. To conclude, we propose a method to automate retinoscopy using a smartphone and patient wearing a paper frame. We also propose a video analysis pipeline which tracks beam and retinal reflex in a video. And finally, we evaluate proposed system on 185 distinct eyes in a real world setting. For more details, please refer to our paper. Thank you for attending the presentation.